My name is Ilya Burenko. I work at the AI lab at Sberbank, and I'd like to tell you about the methods that allow us to improve the segmentation, allow us to improve the matrices to segment X-ray imagery using uncertainty estimation modeling. Now let us begin with the background. Speaking of segmentation, we mean the following. In our case, we're speaking of a deep neural search network. We feed the network an image, and then we ask the model to identify the area which responds to certain characteristics. In this case, we predict the pathological areas, the areas with pneumonia and lung disease, and this solves our segmentation needs. Now, here is the statement of the problem, and here is the inputs and outputs. It is also worth mentioning that there are multiple publicly available data sets dedicated to pneumonia. However, they are quite different to the data sets we used in the following. They either have poor marking in terms of segmentation marking or spatial markings, or in best cases, they just underline the rectangular area symbolizing the stem of pathology in the lungs, and also they're missing the images of both projections, only using a single projection, either frontal or lateral. Our data sets are unique in that regard. We're going to upload it online soon, and it will be publicly available. We have pathologies, we have two projections, frontal, lateral, and every one of the cases in terms of pneumonia was marked by 3 experts.
And every pair, every image was looked at during the research project as an element for the test sampling. And in this slide and some of other slides show the examples of input data, the examples of X-ray views and the marking the doctors made. And we see that there are cases like here where frontal view and the statement and the segmentation and the connectivity is quite high. On some views, it is lower. There are cases where in one view, doctors mark various types of component connectivity. So one radiologist shows 2 areas, another just 1 area. So we have such cases in our sample. From the point of view of machine learning, this is not a very complicated task. You can easily our data set was quite large, fortunately, and we were able to quickly have good results, segmentation results. And on these slides, we show how exactly what the model predicts, and it can be compared with what doctors showed. And we see that in general, segmentation result is quite good. And this is proved by the metrics we have. Sometimes there are cases when the model is predicting 2 connected components instead of 1, but it happens in cases where doctors were not connected, and we took these cases as properly forecasted, but properly predicted. But there were cases when doctors made the marking, but the model didn't give any answer. So this means a problem for doctors from clinical point of view, because X-ray study, from what doctors say, is a study with a low capacity, and sometimes doctors do the following: they analyze front image, and if they do not see or they're doubtful about pathology, they use the lateral view. That's why for doctors it is important that predictions on both views are related. If model predicts something, this should be also there in both views. And in this work, we try to resolve this problem. We try to recover and to create a method that allows you to have connected segmentation on both views. And the model we trained has quite good classification metrics. So we calculated them basing on segmentation metrics. So we do segmentation. If the model shows an area, then the model predicts a pneumonia. That's how we take it. And we compared it against what doctors were saying. And bar 3 and 2, we show the metrics calculated for all views, for frontal and lateral views. And first bar shows the metrics in general. And here the approach is a bit different. If a model for frontal view shows the pneumonia, and this coincides with what doctors say, and if it happens for both views, if front and lateral views and the predictions of the model coincide with what doctors predict, then this is the right answer. In all other cases, it is wrong. In all other cases where we make predictions, we take these cases as not right. So, for instance, the marking area is wrong, or the model does not predict the pneumonia. These cases were just crossed out, and the frontal view shows that the model doesn't give us false positives, and this can be used as a signal to restore the segmentation in the lateral view. If we know that there are no mistakes here, then and we do not miss pneumonia here, then we can try and recover the segmentation in the lateral view. In our work, we do it through assessment of uncertainties. This is an umbrella term, but this means the following. There is a number of methodologies that allow you to make predictions, not just saying that in this pixel there might be pneumonia, but also understand from what range the model makes this particular prediction. And the larger the range is, the lower the confidence in the prediction, and vice versa. Uncertainties can come in two times: aleatoric and epistemic uncertainties. Aleatoric uncertainties come because of the noise in observations. This might be noise, or for instance, it might be a problem of recording data from hardware to servers, or a problem in hardware, and that's hard to control. Sometimes you can change equipment, and this problem will goes away. Epistemic uncertainty can be reduced through more data, but and in this work, we are assessing the sum of both types of uncertainties together, and one of very useful approach in this case is dropout neural networks. They are structured in a very simple way. You do not change anything in the framework. You just put a dropout layer, and you train your neural network. And when predicting, you just keep your dropout network switched on, and you send the same picture, and then balance smoothen the result. And when we are switching it on during predictions, yes, predictions might be different. So this is the input and the output, and we make the smoothing through pictures that are shown to the right. And from information, we know that both types of uncertainties can be calculated as entropy. For prediction, we have general information, mutual information is in charge of epistemic uncertainty, but the last one is not used in our work. Sometimes it so happens that the uncertainty might peak at the border of segmented area, and in cases when model predicts areas that look similar to those segmented by doctors, we see that we will have this level of uncertainty, maximum at the border and smaller uncertainty inside the area of predicted field. And sometimes predictions are not large, and segmentation is not large comparing against to what doctors are segmenting, and the picture is a bit different, and we have the peaking uncertainty inside the area. But what happens in cases when we need to recover the segmentation? And in frontal view, we see that the entropy and general uncertainty is actually showing the same what doctors segmented. This is one case, this is another case, and that's why we decided to take areas with high entropy as an area that should have been segmented. And after this, we have quite good prediction as a result. Here you see this is how this approach is illustrated. To the left, predictions without assessment of uncertainty, and to the right, we recover the segmentation on lateral view through assessment of uncertainty, selecting pixels with high uncertainty for missing segmentation. And this is another case illustrating our approach. And at the same time, so far, this approach has its drawbacks. On the picture to the right, you can see that doctors' segmentation is not in line with what model says. But we need to make one comment here related to the following. Two other doctors, for this particular case, segmented a larger area, and it coincides with what the model predicts. So for some cases, there are no overlapping areas with the model, but this is not true for all doctors. And in this table, we show that such approach towards recovery of segmentation improves our segmentation results. So, proper prediction is a prediction where marking made by the model overlapping with the doctor's ones is not empty in frontal and lateral views, and all classification metrics grow dramatically. We should compare bar 1 and 2. We also compare approach I described related to assessment of uncertainty through dropout methodology, Monte Carlo dropout. We also decided to compare it against another approach of assessment of uncertainty that allows us to, where an ensemble of models are learned through adversarial attacks, and the results are quite comparable. But then the question is which one to select. The ensemble takes more to be trained, and predictions, in terms of predictions, they can be faster. But the methodology I described with assessment of uncertainty, it takes less time to be trained. But when we should recover the marking, this process takes a long period of time. But depending on what methodology is more convenient for doctors, you select the one you need. Thank you very much. That's it from me. Yes, Ilya, thank you very much. One short question, please, very briefly. Do you plan to use such methodology for other types of data, other modalities? Well, obviously, yes. This can be used for other modalities, but probably for us it might be more interesting to use it to detect pathologies that the model cannot see during training. It is an interesting task for us. For instance, if we train a model to segment pneumonia and it can say probably this is cancer, this is an interesting task for us. But yes, it can be used in other modalities also. Thank you very much. Very good, colleagues.